We are back again. I am on a roll. This is like a 24-hour session, and I'm just going at it like crazy here. All right, so let's get started here. We're in section 4.5. We're going to try and make some connections. We're at the end of chapter 4. Yippee, right? So today, we're looking at being able to make the connections between what we're already starting here. So we should see ways to simulate randomization samples for a variety of situations, okay? Technology is what we're going to utilize here. So we're going to talk about multiple ways to do that. Single proportion, 3 out of 7 things. Difference in proportions, 2 groups. One group has a proportion, another group has a proportion, and we're going to calculate the difference in those proportions. Single mean, difference in means. This would be observational studies. So in an observational study, I have 2 categories, and in one category, somebody gets one value. I'm going to measure that proportion. Another control group doesn't get that value, so I am going to get another mean, and then I'm going to get that value from that mean and a correlation. Along the way, we'll make some connections, I hope. Data collection and randomization distributions are our keys. Bootstrapping and random distributions are our tools. Confidence interval levels and hypotheses tests will be part of what's going on here. So all of these are words that we have used. All of this is things we already know how to calculate, and now we need to bring it all together and make something happen with it. It says on a randomized distribution that a p-value can be calculated by randomization distributions. So if we stimulate many samples, assuming H of O is true, and we calculate the statistic of interest for each sample, we can find the p-value as the proportion of simulated statistics as extreme as the observed statistic. This is the curve. This is the dots that are happening on the extremity of a distribution. So if I have a center, some H of O value, and I'm stimulating results, and I get results over here in the tail, remember that p-value is the proportion of simulated statistics as extreme as the observed statistic. So it matters if it's right tail, left tail, two-tail test. It says today we'll see ways to simulate these randomized samples for a variety of situations, and the common goal for this is distribution is to match the null hypotheses. It says the main criteria to consider when creating randomized samples for a statistical test are: be consistent with the null hypothesis, and 2, use the data in the original sample. So we have to replace and restat it. Replace and restat. Ideally, we also try to reflect the way the original data was corrected. Okay, so we don't want to go off the curve basically and start making up brand new stuff here. I think we talked about this a long time ago. There was this octopus, Paul the Octopus, and in 2008, Paul the Octopus predicted 8 World Cup games. He got them all right, and all of them were correct. And it says the evidence of Paul's chance of guessing correctly if p is really greater than a half. Well, why is p greater than a half? Well, if Paul was just simply randomly getting the answer right or the answer wrong, and let me back up. So they had 2 tanks. So you can see in the picture they had 2 tanks, 2 teams playing in the World Cup, and the octopus landed on top of the one that was going to be the winning team. And he did this 8 out of 8 times. Okay. What if it was just by chance he got it right? Well, by chance he gets it right, it's 50% of the time. It's either right or it's wrong. It's one of the two. So when we look at the evidence of Paul's chance of being correct, what is the chance that he was actually, that 8 out of 8 was really a good number for Paul? Okay, so we use the words like, for instance, how unusual is it to see a sample statistic as extreme as the observed? And in Paul's case, it was 8 out of 8, or 1 was the case. It says we need to know what kind of statistics we would observe just by random chance if the null hypotheses were true. How could we configure this? Well, when we talk about this, we have to talk about a couple of different things. We have to talk how to stimulate these examples and how to get values. So we have n size of 8 with Paul, because 8 different trials, and anything greater than 1/2 would be 0.5. So we're going to go do this real fast. And again, StatKey is our tool for this. Moment to switch out of here and go to stat key. And I get to stat key. All right. So we're in stat key. And first thing we have to do is talk about a parameter of interest. Okay, well, my parameter of interest is going to be a single proportion, right? Single proportion. And in this single proportion, I'm going to look at editing data. Okay, so if I do some data editing and I crank, I'm going to see if Paul the Octopus is actually in here, and I'm not quite sure. Oh, Paul the Octopus is. He's right there. Paul the Octopus forecast. So I'm going to generate 1,000 samples. There's 1,000 times. Notice that the null hypothesis is 0.5, right? 0.5 right there. Nothing going on 0.5% of the times. We're asking how unusual is it that Paul's value is greater than that? Okay, because how many times will he be greater than 50%? So we'll right-tail this test. Now, when we look at right-tailing this test, though, Paul the Octopus didn't get a statistic of 0.875. Paul the Octopus got a 1.0. He got 8 out of 8. When I calculate 8 out of 8 times, and then I look at the p-value, which is associated with 8 out of 8 times, Paul the Octopus has a 0.004 value. Now, you may run this test and you may get 0.002 or 0.003, but no matter what 0.00 something you get, that's an extremity that's happening. That's extremely rare in all, remember, alpha levels. So to use technology to do this is a very useful tool. And so how extreme is this? Okay, well, and when we talk about this stat key and we talk about this generation, and here's a slide taken from it, to have that p-value, remember, what we're looking for is that the p-value is less than the alpha significance. That's what we're trying to stimulate. That's what we're trying to say is going to happen. Okay, so we are, in this particular instance, are looking at Paul and, hey, how extreme is this to happen? So it says, there's a question here. I got to click on it to get it up there for you. Based on this, do you think that a probability of 1, that's Paul's number, that's a statistic, with n of 8 is statistically significant? Well, yeah, we have to say yes. We have to say yes. Why do we have to say yes? Because that value of 0.00, and I think I got a 2 is what I had, or a 4, whatever it was, it's less than any alpha level that I can come up with, whether it be 0.01 or whether it be 0.05. Doesn't matter. We have a question number 15 here. Finger tapping and caffeine. It says we look at some finger tapping rates to see if ingesting caffeine increases the average tap rate. So people tapping their finger on the counter, and we're going to give them more caffeine and see what happens. It says a sample for 20 subjects, 10 randomly getting caffeine and 10 with no caffeine are given in the table below. To create a randomization distribution for this test, we assume the null hypothesis is equal, or caffeine minus no caffeine is 0. It says that there's no difference in the average tap rate between the caffeine and no caffeine groups. Okay. So caffeine measurements across the top with a mean value, no caffeine across the second row with a different value. Create one randomization sample by randomly separating the 20 data values into 2 groups. Find the sample mean of each group and calculate the difference xc minus xn in the simulated sample means. So they want us to do 2 things. One, they want us to be able to calculate a mean value. And 2, they want us to be able to find the difference between those 2 values. All right, well, first of all, if I have to calculate this value, so let's see how to get this mean value. And I already taught you this at the very beginning of the course, but probably now is a good time to return to trying this and see what we can bring back. I'm going to stop the computer for just 1 second. I'll be back with you. I'm going to get my calculator, so you might want to grab your calculator. Okay, I'm back, and I've got my calculator open, and we're going to put some stuff into the list, right? So we're going to go to second, and we're going to go to the list. if you look at the list options that I have here, and we've done a couple of things with lists, we got operations, things like that. In order to get data into the list, you don't go second list, you go simply list, okay? So I'll do that for you one more time. Some people have asked me, and that's why I have to show you this. Pushing the stat button gives you the editing option, but if you hit second in the stat button, well, you get to the operations buttons. Those are two different areas. We want to be just in the stat button right now. Edit number one. So first of all, if you need to clear your list if you haven't already cleared them, remember to clear a list, you go up top, you hit the clear button. Right here, you hit clear and you hit enter, and boom, everything will go away. So we're going to put this this pile of data into here. So we're going to put 246, 248, 250, 252, 248, 250. I'm just going to do one of these. 246, 248, 245, and 250. So I've got 10 different things, and hopefully I've put all my data in properly, kind of faster. Now I'm going to go back to that second list function. Okay, I'm going to look at second data. I'm going to scoot over, and I have a lot of different things going on, right, in here, and we can do some operations, and I'm showing operations and everything, and I want to show you where there's some different features at, what we can do, okay? So let's clear everything, make it all go away. Hit the stat button, scoot over, calculate. So I went to stat, I went to calculate. I want number one variable statistics. I want to point it to list number one because that's where I put my data. I want to hit enter a couple of times, and voila. Here goes my mean, 248.3. So you will have to calculate your own mean value. And the way you calculate that mean value is the way I just did it, and rewatch if you need to. But we now can see that how they got the 248.3. So it then says, hey, what is the difference in the simulated samples as given? Okay, well, we need to take the x of c, which is 248.3. We need to subtract from that the 244.9, and we need to get the difference in those two values. And if you subtract those two values, you get 3.4. So the difference in the simulated samples is 3.4. That's our statistic. That's why it's important to have that statistic. When we go to different questions, we need to be able to calculate that statistic. We haven't done anything as far as testing it yet. Question 16 is exactly what I just did in question 15. So I'm going to leave question 16 for you. However, though, watch, different people have different data sets. Enter this data set into L1 and then run one variable stats, and that will be able to get your sample mean. And remember, your sample mean is your X bar, okay? And then it wants you to translate the original sample by the appropriate amounts to create a new data set, okay? How this is true. So they actually want you to, suppose that you increase something, and if you change something, it's like this. It's similar to this question. If I took 1 and 2 and 3, and I took those numbers and added them up. 3 plus 1 is 4. 4 plus 2 is 6. Total is 6. And if I divide it by 3 different things, the average is 2, just to keep it simple. If I increased all by 10, so if I made it instead 10, 20, and 30, and I again added those all up, that's 60, right? 30, 40, 50, 60. And I divided that 60 by those 3 things. Well, now I've got an average of 20. It's still my same number. It's talking about the effect of sample size and the deviation. The deviation is what this question is referring to. And when you look at the standard deviation, the standard deviations will be similar to their retrospect. Okay? I'm going to let you walk through this question. If you have questions on this, you can certainly ask me. I want to get to this one because this one's in StatKey, and this one's pretty useful for us. It says that a restaurant chain is measuring the levels of arsenic in chicken. Did you know that there is actually acceptable arsenic levels in chicken. I had no idea until I started reading about it. And there's a certain amount of arsenic allowed to be in your chicken that you buy and eat. The question is whether the evidence that the mean level of arsenic is greater than 80 parts per billion, greater, so it'll be a right side tail test. So that puts H of O at exactly 80 versus H of A at being greater than 80, where mu represents the average level of arsenic in all chickens from a certain supplier. It takes money and time to test the arsenic, so a sample of Ed equals 6 chickens from one supplier is tested, and the resulting sample mean was 91. So they're interested in finding what happens when we have this particular value. And I'm going to show you how to put this into StatKey and how to run these numbers. Okay, so I'm going to switch out of the computer again. I'm doing a lot of switching out of the computer today. And I'm going to go back to StatKey. And I'm going to get to the beginning here. These are mean values. So randomization, single mean. I'm going to see if arsenic chicken is in here. Arsenic chicken right here, second one down. I'm going to run 1,000 samples like it tells me to. Here's the distribution of 1,000 samples. Now, when I look at my data values and I look at running my data values, I'm looking at pulling a p-value of 3 decimal places, and I'm looking for that x value of 91. Where did I get that at? I got that right here. They had a sample mean of 91, and we want to know how unusual that is to have that sample mean of 91. So I ran my 1,000. I know it's a right tail test because I want greater. I'm going to go down to the 99, and I'm going to change it to a sample of 91. That was my sample. Right here is my p-value association. I ran it at 0.139. Again, remember, you can get different results. Why can you get different results? Because a random test can show different results. So when I ran my p-value was what was that just now? Just 0.139. I gotta go back and get it. I'm sorry, because I already forgot it. 0.139. Okay, great. 0.139. Let's go back to it. So rounded to 3 decimals, I have a p-value of 0.139. Again, yours could be slightly different. 140, 141, 142, 120, 116. What is the conclusion if you're testing at a 5% significance level? Okay, so here's what you're comparing. You're comparing 0.139, and you want to know if it is smaller than 0.05. Oh no, it's greater. So what's your conclusion? Do not reject. You can't reject because your p-value was larger than your alpha significance level. Should the restaurant chain stop ordering? No. No, they should not, because they did not find anything significant. Choice of statistic. It says, by default, we often choose to use the difference in proportions when doing a randomization test for 2 categorical variables. Remember, things in categories. We take those from a two-way table, and in a two-way table, we calculate a proportion. So we take group 1 and we take its proportion away from group 2. However, we could just as easily use almost any other statistic. We could use average, and we could use row or correlations when we're measuring. It doesn't matter. In a randomized experiment of randomness is the random allocation of the treatment group. Okay? So it says if the null hypothesis is true, remember, nothing going on in the null, the response values would be the same regardless of the treatment group or the assigned group. We really should have the center of the data, no matter which group we're in, of nothing going on as being the same. There shouldn't be a difference in there. It says to simulate what would happen just by random chance if H of O were true, we reallocate cases to the treatment groups, keeping the response values the same. We reallocate cases. So we move these cases around into the treatment groups, and we look at the responses the same to see, are we seeing significant results in the group that is receiving the experimental notation, or do they differ from the control group? We're really looking for differences here is what we're looking for. It says in observational studies, the randomness is random sampling from the population. Because remember, we're not performing a statistical test, we're simply observing. To simulate what would happen just by random chance if H of O were true. We simulate resampling from the population if H of O is true. Remember, this is referred to as bootstrapping. So we keep putting it back in and saying what would happen again, what would happen again, and what would happen again. How do we simulate this resampling from a population when we only have one sample? Remember the bootstrap design, right? Well, the question is, how can we generate random samples for observational studies? Well, for just observing things, then all we have to do is really simply make H of O true. If we make H of O true and we regenerate multiple samples with bootstrapping, then we are going on the assumption that H of O is true, and all of the data that we pull over and over again is the bootstrap statistic, which is looking at the data to say, hey, I have said that H of O is true. Here's a good design for this. It's very theoretical right now until we actually start to see some examples. So stay with me. It says mu, the average human body temperature, is 98.6. So H of A it's not 98.6. It could be higher, it could be lower. So let's say that we run a sample statistic and we get a 98.26, okay? So we have a stat and we really want to know the unusualness of 98.26 compared to 98.6. Well, we can make them all true just by taking or adding 98.6 minus 98.26, which is a 0.34 degree difference. And we can take that and we can adjust all data values by 0.34 degrees. Bootstrapping does this very same thing. It says, hey, listen, if null is true at 98.6 and you really got a 98.26, you were off by 0.34. Well, rather than letting all of the data be off by 0.34, bootstrapping goes to the problem, adjusts it by 0.34 degrees, and reruns the data and says, remember, the spread of the data should be similar between the sample and the population. Well, now we're assuming that H of O is true, so we're taking our bootstrap design and we're telling this bootstrap design, hey, if I adjust the center and make all the data true, H of O true, then I can make an assumption about the original sample, and the original sample can make an assumption in its spread about the population. That's really what we're talking about here. We're just bringing it up a level. It says in StatKey, when we enter the null hypothesis, the shifting is automatically done for us, okay? The shifting is automatically created for us, and it does all of the work for us. I really don't need to show you that. It happens. When a null, for instance, of 98.6 is taken place, that is my null hypothesis of my center. So all the data calculations have gone in under the randomization dot plot and made that null hypothesis a true statement. Remember, you can change that null hypothesis value to something else. This can be edited if you need to adjust your null hypothesis, and it will automatically do the data for you. That's what you got to love about StatKey. Oops. And it does give a question here. It does talk about a p-value. Remember, this is a two-tailed test. Remember, a p-value here, on one end, it's 0.001, and this is a two-tailed test. So therefore, 2 times 0.001 or 0.002 is the true p-value. A two-sided test always uses two sides of a p-value. Paul the Octopus, that single proportion, it's like flipping a coin 8 times. A cocaine addiction, a randomization experiment. It's a re-randomization case to treatment groups where we keep the response values fixed. Okay, so we can look at a randomization experiment and we can say that the control group and the non-control group should have the same center, and we're looking for a change in what's taking place. Body temperature. If you're measuring something in body temperature, it's a single mean. Okay, so we've looked at three things so far. Paul the octopus, a single proportion. We had a randomization experiment in which we compared two cases. We have a body temperature, which is a single mean. We're shifting this H of O to make it true. All of these exercises are moving the observational study and shifting H of O to make it true, and then bootstrapping. Again, when we get to it, it's so that this curve's, the spread of this curve in the bootstrap will be similar to the spread of this curve in the population. It's what all of these slides are determining and talking about. So let's talk about regenerating some samples. It says the specific method varies with the situation, but the general idea is always the same. Simulate samples assuming the null is true. And remember, this assumption word means that adjustment has taken place. You don't have to worry about doing it. You just have to understand that it's happening. As long as the original data is used and the null hypothesis is true, then the methods usually give similar answers in terms of p-value. Similar, right? Similar. I run the experiment, I get 0.002. You run the experiment, you get 0.005. That's similar. Okay, that is similar. Technology generates this randomization for you. Most important is not understanding how to generate it, samples, but why to generate it. Again, why? To make H of O true. I've said that like 17 times today. It says a test for a proportion. We sample from the population with the null proportion using sample size in the original sample. But if we test for a mean, it's to keep the variability of the simulated sample the same. Okay? We shift the original sample so the mean of the shifted value is the null mean. All we're changing here is words. We're going from a null proportion to a null mean. And if we're taking the difference of two means or the difference of two portions, then our null is at 0. And here's where we are. A test of difference in means and differences of proportions. The same explanation for both comes out as the results of the randomized experiment. To match the null assumption of no difference, that's the word I just used with you. I made it so super simple. Look for 0. We want the difference between the groups to be nothing, okay? Nothing. And that's why when we center up a null hypothesis on the difference of means or the difference of proportions, we center it up at 0. It says a test for a correlation, so we're just into the other type here, is to match the null hypothesis of a 0 correlation. We randomly assign the values of one variable to the values of another. Why 0 on a correlation? Because remember, if the correlation is 0, absolutely nothing is going on. A correlation of 1, everything is going on. So we created a bootstrap distribution for body temperature. And average body temperature resampling replacement from the original sample of 92.26. Okay, so first of all, so if we take a look at this, and this is a bootstrap distribution. A bootstrap distribution is always centered up on the bootstrap center. The bootstrap center is the X value. Okay, when we look at bootstrapping, we're looking at centering up in the middle data values of what's happening with our statistic. And you can see that this proportion that we're generating around, what we're looking for is the curve. We're not looking for the center at serves so much. We want to know, how is this distribution, this spread, going to compare? And by the time I get done with all of these in 2 more slides, you'll see what I'm talking about. If we look at a randomized distribution of 98.6 and we add all of the 0.34s, remember we make the null true. This is a lot of jargon to say. I'm going to back up one slide. When you notice this curve and you notice this curve, and we put them side by side, we're going to see major comparisons between the two. Now, remember, the null is at the center of this particular placement. Okay? The null is true, is at the middle. If nothing is going on, the body temperature is 98.6 degrees. We center it up on the null. And if you look back at the last statistic, we center up at the data. Okay? The bootstrap revolves around the data, whereas the distribution of the null or of the population centers up around the null. So put them together and look at them. If we look at them, the bootstrap centers at the sample statistic. I'm going to write that up here. This one is all about the sample statistic, the bootstrap sample statistic. Okay? Bootstrap distribution goes around the sample. Whereas the randomization center is always around H of O. The randomization distribution is interested in H of O. We're not, and those are two completely different numbers. However, I mean, because if you look at 98.6 right here and 98.06 down here, or in essence, the center, 98.29, those numbers are not the same. However, what you do see is that the curves are super similar. And that's what we look for when we look for in using Bootstrap. Bootstrap, this curve helps make this curve on a new center. And what is that new center? H sub O. And you can see the centers are different completely, but the spread is what we are concerned with. It says these two distributions are identical up to random variations from simulation to simulation, except for the center. Again, Bootstrap at the statistic, at the sample, and distribution of the null around the center, which is H of O. It says the Bootstrap's distribution will be centered around the sample statistic, 98.26, because that was the measurement that was taken, while the randomization distribution will be centered around the null hypotheses at 98.6. The randomization distribution is equivalent to the Bootstrap distribution, but shifted over. The distribution to standard errors left and 2 standard errors right. The distribution will be similar between the two. Using bootstrapping, we found a 95% confidence interval. Remember, center plus or minus 2 SEs, or 1 ME, of 98.05 to 98.47. This does not contain 98.6. So when we used our data from our bootstrap, we determined that the low value and the high value for the 95% CI, remember, confidence interval level, we found it to be somewhere between 98.05 and 98.47. What you don't see in there is 98.6. So at an alpha level of 0.05 or a 5% alpha, we would reject H of O. No picture. We are basing our data primarily on that our stat is outside of the CI. If you are outside of the CI, then we can reject that value. And our stat is our mu of 98.6. It doesn't even fall within inside of our confidence interval level. In these values, all we're really doing is changing our H of O and our H of A to a more desirable mean, so that we can look and put that H of O within inside of that confidence interval level. We want to run the data, but looking at the previous slide, our data is not even within inside of it. That 98.6 isn't even in there. But we know that confidence interval is correct, but we just haven't yet saw that it's not centered up on the proper middle. So this random distribution helps us out and helps us fall within the values that we need to. And again, here goes our center, and here goes our centers. And we can see that our distribution there falls. If we're testing using an interval, it says a confidence interval represents the range. I'd like to circle that for you. A range of plausible values, a low and a high, if you will, folks, for the population parameter. Remember, the population is the big group. If the null hypothesized value is not within, circle that, not, is not. If that thing is not within the CI, it is not plausible and it should be rejected. If the null hypothesis value is within the CI, it is plausible and we should not be rejected. Remember, we're judging the null hypothesis, the nothing going on, against a confidence interval level that we have gained by bootstrapping. Nice roundup here. If a 95% CI contains the parameter in H of O, then a two-tailed test should not reject H of O at a 5% significance level. If a 95% CI misses the parameter in H of O, then a two-tailed test should reject H of O at a 5% significance level. What this tells us is that you are outside of the CI, we're going to reject you. If you're inside of the CI, we're not going to reject you. Let's look at this in practice. So it says use the CI to state the conclusion. We're going to reject or do not reject. Of the test sample given, we have a significance level used. So our data is nothing going on, 0.7. And we want a two-tail test of H of A to equal that the p-value is not 0.7. So it can be higher, it can be lower. At a 95% CI for 0.65 to 0.82, our first alpha level. So first of all, we're determining the alpha level based on a 95% CI. Well, that means that we're going to have, I'm going to get all of these on here first. There we go. So on these top ones, we're determining just simply the alpha level. Well, a 95% CI gives us a 5% alpha level, or 0.05, because it's the counterpart of 95%. Same goes for part B. Now, would I reject or would I not reject? Well, first of all, if I have a data value of 5% and I have a 0.07, then I do not reject. I do not reject. And that's based on the fact that this 0.7 was inside of 0.65 to 0.82. I go to the next one, part B. Part B says, hey, your alpha level, what is it? It's still 5%. But this time, I am going to reject. Why am I going to reject this time? Because 0.7 is outside of this number. It is not in that number. In the next one, 0.7 is clearly inside of this alpha level. So I am going to do not reject. But this time when I do not reject at a 1% significance level. To not reject at a 1% is far superior to a do not reject at a 5%. Again, I'm rejecting based on inside or outside, and I'm determining the alpha level because of the CI. The CI tells me what the confidence interval level is, or what the alpha level is. Three more, sorry. So my first one, I'm simply on this one figuring out what do I have for an alpha level. So my alpha level in the first one is 10%. It's 10% because I have a 90% CI happening right there. And when I take those values and I look at those values, I have a P1 minus P2 from 0.4 to 0.18. Okay. Well, in letter A, I'm going to have to reject. I'm curious if you know why I'm rejecting. Oops, I spelled sorry. Obviously, I can't reject. Sorry. My eraser is not working for me. It's rejecting me. If I take P1 and I minus P2, that equals 0. And remember where my range was at. My confidence interval level was 0.04 to 0.18. 0 is not inside of my area. And I'm rejecting at a 10% level. If I do the next one, I'm doing P1 minus P2 again, 0. And this is a greater than value. And so this is a one tail to the right. One tail to the right. First of all, I'm going to have a 5% significance level. Why am I going to have a 5% significance level? Because I only have half of the tail now. Remember, there's 5% on the left and there's 5% on the right. Okay? And this was a 90% CI, and a 90% CI left 5% on the left and 5% on the right. And again, I'm going to reject because I'm outside of, my value is outside of that greater value. Kind of the way you want to think about it is 0 is not greater than that value on that right side. Because remember, 0 is still my statistic. When I go to the letter C, I'm on a left tail. So remember, I'm looking for data which is to the left of my CI. Remember, my CI is normal, 0.04 to 0.18. I have a data value still. I haven't left a data value of 0. So now I'm looking to see if 0 falls within that number. Okay, well, 0 does fall below 0.04. So it's definitely in there. So I do not reject that because it's in there, right? I'm looking to see, is 0 in that value? Well, it is. It's below it. It's good. And I'm also at a 5% level because I'm on a one-tail test. Again, I'm analyzing to find out if 0 is inside of my number. And when 0 is inside of my number for less than, because it's below that, I'm rejecting basing on that alpha level because it's down in that tail. And in letter B, I'm not finding it. I'm rejecting it because I'm looking above it, and 0 is not above it. You can also, let me change my color here for a moment, if I can help you out. Remember that here, we're measuring from 0.4 up to 0. Let's say 18. And when I'm measuring less, 0 is way out here. So my 0 value, when it's below, is in there. So I am not rejecting that value because I was looking for the alternative. Intervals and tests. Let's continue. And rejecting's an H of O really just takes time of practicing. You'll get better with it. Do the Wiley stuff and it'll come to you. A confidence interval level are mostly useful when you want to estimate a population parameter. That's really what we use these things for. A hypothesis test and p-values are most useful when you want to test a hypothesis. So let's make sure we know that difference. Do you want to estimate something? Do you physically want to test something? Use a hypothesis to test and use a parameter to estimate. Confidence intervals give you a range of plausible values. P-values quantify. A range is not the same thing as quantification or evidence. Those are two different things. Here's a nice layout, really, if you will. A bootstrap distribution, you create repeated samples, you do replacement, you do your best guess, you find a CI, and you center it up around the observed statistic. Bootstrap. You do all the same stuff on a randomized distribution, but now the null hypothesis is where we're centered up at. And a null hypothesis will be more of a randomization. The big difference is, down at the bottom, that a randomized distribution assumes H of O is true, while a bootstrap does not. A bootstrap just simply goes and centers itself up on the data, and it doesn't care what H of O is. A randomization distribution does care what H of O is. Two values here. It says let mu be the average amount of sleep that a student gets, and it gives us a sample of 6.7. And then it gives us a bootstrap distribution, and it says we're supposed to pick between these two things. All right, well, we're going to go to these two things, and we're going to look. First of all, I'm going to find the middle. If I look at the middle's at 6.7. 6.7 was the statistic. The one on the left-hand side, A, is definitely the bootstrap. Mu would only come in when you were looking for a non-bootstrap or a distribution. Now I'm looking for the random distribution. So you can read all the data and you can see it. However, though, the random distribution value is always going to be centered up around something greater than 1/2. Okay, well, I have two distributions here. One of them, the middle, is at 1/2. One of them, the middle, is at 0.7. Remember, a random distribution is always at the null. The null, H sub O, is that P is actually equal to 1/2. Getting a little crazy on my pen there. So my choice is letter A. Randomization distributions. In hypothesis testing for mu of 12 and H of A less than 12, we have samples of N45 with a sample of 10.8. Question number 1. What do we require about the method to produce a randomized distribution or a randomized sample? Well, in order to have that, we got to know where the center of it is, and the center of it is a mu of 12. We don't want B because that would be the alternative. We don't want C because that's a statistic. Number 2, where will the randomization distribution be centered? All right, well, the center of all randomized distributions are the mu value, 12. Number 3, what will we look for in this randomized distribution? Well, what we're going to look for is if you have a center of 12 and you randomly distribute, how extreme is it for the statistic that you have of 10.2? So we'll find 10.2 on the scale, and we'll measure the statistic against the null hypothesis. Next slide. So we have a similar question here. H of O, mu1 minus mu2. So HA is mu1 greater than mu2. So we have a right side tail test. We have data statistics at 26 and 21. What do we require about the method to produce a randomized distribution? Okay, so if we look at this particular one, remember, we want this. What we need to know is what is mu1 equal to mu2, which is the same as mu1 minus mu2 equals 0. So we're going to center up, and that's question 2 actually. We will center at 0. Again, I've done this for you. I think this is 17 times now. Mu1 minus mu2 is equal to 0. A little bit of algebra. Number 3, what do we look for in the randomization distribution? Do we look for a standard error? No. A center point? No. How extreme is 26? That's just one data point. How extreme is 25? Again, that's just one data point. Well, how do I get the data point? Well, I'm supposed to take x1 minus x2, which really is going to be equal to 26 minus 21, which is 5, and 5 is what I'm looking for. How extreme is the difference between x1, data point 1, and data point 2? I'm going to need an iced tea after this one. We're going along here. What is the proportion of people using a public restroom wash their hands after going to the bathroom? These are not the kind of questions I like to answer or look at. However, our questions here are, is this a CI? Would you use a hypothesis test, or is it neither? Well, a proportion of people, we're looking for a range. We're looking for a CI. Okay. In a CI, we're looking for that interval of things that take place. Okay. We're not testing anything here. B, on average, how much more do adults who play sports in high school exercise than adults who did? Again, we're not testing. If you're not testing, it's a confidence interval level. What's the range of people who are more? It's a right side one, but that's okay. In 2010, what percent of U.S. Senate voted to confirm Elena Kagan as the member of the Supreme Court? There's no CI here. We're not looking for, what are the range of people. We're not measuring anything. This is just simply an inference. So this is a neither. Nothing, there's no range of data values. It's not what percent of the population would vote for. It is just simply, hey, who did? And we're taking a measurement. Letter D, what is the average daily calorie intake for 20-year-olds? Again, CI. You haven't produced a single statistical test yet, or we haven't. Letter E, what percent of U.S. voters support the institution of K-12 math curriculum? Again, where is that range, and how broad is it allowed to be? On average, there were 23 players on the U.S. Canadian hockey team, older than 23 players on the. There's no relevance here. It's 23 players on this team, 23 players on that team. It's just a proportion between them. There is a neither statistic here. Now, letter G, you'll see letter G on a test somewhere. Do a majority of adults riding a bicycle wear a helmet? Now, this is actually seeking evidence, right? We are looking to answer a question. And I know this is different because it seeks an answer. It's not just simply looking for you to spit out a couple of numbers and two things fall in between it. This is actually a hypothesis test. This is the only hypothesis test that we have on this page. Everything else just simply wants a summarization. Remember, look for seeking evidence in order to find a hypothesis test. All right, let's summarize this thing. Randomization samples should be generated. They should be consistent with the null hypotheses. Remember, randomization. Using the observed data, reflect on the way we are taking the data. If the null hypothesis value lies inside of the 95% CI, and then a two-tailed test using alpha of 0.5 would not reject. If you are inside the CI, we won't reject. If the null hypothesis value lies outside of the 95% CI of the two-tailed test using the 0.5, then we would reject.